So I want to look at a well-known algorithm for solving the minimum spanning tree problem that's referred to as Prim's algorithm. But first off, I want to talk about some missteps I made in my previous example. So I ended up wasting a lot of time. So let's look at an example. Okay, from our earlier example, if you remember, we started at San Francisco and we identified our first outgoing edge, which went to LA. So as I was working through the problem, I was somewhat focused on the outgoing edges. Prim's algorithm actually focuses on the vertices that are not yet connected, and in doing so is able to reduce the number of edges that we have to consider at any one time. Okay, so Prim's algorithm. First of all, let's take a quick look at the Wikipedia article on it just to get some background. So first off, Prim's algorithm was actually invented by Jarnik before Prim, or at least discovered. So multiple people get credit for this, including Dijkstra. So this is a well-known algorithm. It's been discovered and rediscovered multiple times. You could even call it the DJP algorithm. Okay, so there are also other well-known algorithms, including Kruskal's algorithm, which we will also look at. Okay, so let's take a quick look at basic structure of Prim's algorithm. Okay, so Prim's algorithm is similar to an algorithm that we've seen in the past. It processes vertices, so it's got a loop that will loop through and initialize each vertex. First off, it's going to somehow indicate that it's unconnected. And then we've got some sort of start vertex. And again, remember, we're creating a spanning tree. It's eventually going to hit every vertex, so it really doesn't matter where we start. So if we're at our start, we'll indicate that its distance is 0. Otherwise, we'll update its distance to be infinity. So we're going to assume that we can't reach everything, and we'll slowly kind of expand out from our start, figuring out what we can reach. Okay, so we will insert all of our vertices into a priority queue. At this point, we could also keep track of edges by somehow having an edge associated with a vertex. So basically, the edge would be the edge that is kind of the incoming edge in our spanning tree. Okay, so this is the initialization step. Next, we go through and we process vertices. So we're going to continue going while there's still vertices that are not connected. We'll continually extract vertices from our priority queue, so we'll get them kind of in order of the lowest cost. And then we'll go through each of their outgoing edges of our vertex, and we'll see if the outgoing edge is connected to something that's not yet connected to our spanning tree. And if so, we'll use that outgoing weight, that outgoing edge's weight, to see if it's a good path, if it's better than the best known path. And if so, we'll update the overall distance that we can achieve to get to this new node on the opposite side of our V node, and update the corresponding priority. By the way, this would be kind of the step where you keep track of the edge that's being used as well. So if you're truly building a spanning tree, you're mainly focusing on constructing a set of edges, and this is one of the places where you're changing which edge might be selected for your final set of edges. Okay, so let's go ahead and work through the example that we've seen before. Okay, so here's our familiar problem again, our power line sort of graph. I'm going to use this table here to represent my priority queue. So it's a table of the vertices, and I'm keeping track of the corresponding distance, which will represent the priority. Also, I'm just going to kind of mentally keep track of which edges get used. In reality, as we'd be updating the distances here, we would also somehow keep track of the edge that's capable of achieving that distance. Okay, so step 1, initialization. Again, I'm going to start out at San Francisco, so I'll initialize it to be a distance of 0. I'm going to check off the cities once I've actually connected them to my graph. I'm going to go ahead and initialize everything else to be an infinite distance away from San Francisco, as far as I know. Okay, and now we get to the body of a loop of Prim's algorithm that removes a vertex from the priority queue at the highest priority, which will be San Francisco. And then it'll look at all of the outgoing edges and the opposite vertex, and updating our estimates of distance to that vertex, at least if the vertex is still unconnected. So from San Francisco, we'll look at all of our outgoing vertices. We've got, outgoing edges. We've got an edge going to Boston. We can get to Boston with a total of 2,500. So we'll go ahead and update our distance there. We've got an outgoing edge to O'Hare. So we'll go ahead and update that as well, 1,800. We've got an outgoing edge to Dallas of 1,100. got an outgoing edge to LA of 300. Okay, so we've now processed San Francisco, so we'll mark it as being connected. Okay, now we'll repeat the process. So we'll remove our highest priority item, which is LA. I'm also, again, going to kind of mentally keep track of which edges are being used. In reality, when I selected the 300, I would have stored away which edge was capable of achieving that. Okay, so we'll process LA. We'll look at all of its outgoing edges. So it's got an edge back to San Francisco, but San Francisco is already connected, so there's no need to worry about that one. It's got an edge going to Dallas, so we'll go ahead and update that. It's no better than this. So we've got these two different options to get to Dallas with 1100. And then there's an outgoing edge to Miami. So it's a total of 2300, which is better than infinity. So go ahead and add that in there. Okay, so we've now processed LA. Now we're going to look at our minimum remaining item. So let's see, 2500, 1100 of infinity, 2300, 1800. It looks like our trip to Dallas is our best choice. So if you remember, we actually had two options to get there, but this is the one that got added first, and this one didn't get added because it wasn't actually better. So I'm going to go ahead and indicate, take that path to Dallas. Now we'll go ahead and process Dallas. So we'll look at all of the outgoing edges. And again, I'm going to ignore if the opposite vertex is actually already connected. So we can get to Chicago O'Hare with a total of 800. That's better than 1800, so I'll go ahead and update that. We can get to JFK with 1400. That's better than infinity. We'll update that. Let's see, we can get to Miami with 1100. It's better than 2300. Update that. And we can get back to LA with 1100, but LA was already connected. So again, I'm going to ignore that. Okay, so we're done with Dallas. So next we go through our priority queue yet again. So we've got 800, 1100, 1400, 1400, infinity, and 2500. It looks like O'Hare is our best choice. So we'll go ahead and look at that. So we'll update our outgoing distances. So we've got an outgoing edge to Boston at 700. That's a lot better than 2500. We'll update that. JFK at 600. So we'll update that. Baltimore at 600. Oh, it's better infinity. Then we'll update that. That's great. We could go back to Dallas-Fort Worth, but again, it's already connected. We could go back to San Francisco, but it's already connected. So at that point, I'm done processing O'Hare. Looking down at our remaining vertices, we've got 1100, 600, 600, and 700. So again, we've got a tie here, 2 or 600 apart. It's kind of arbitrary which of these we pick. I'll go ahead and select Baltimore as our choice. So I'll highlight which edge got us there. And then we'll go ahead and process Baltimore. So we've got an edge of weight 200 going to JFK. That's better than 600, so we'll update that. Then we've got an edge of 900 going to Miami. That's also better than our current estimate, so we'll update that. And with that, we're done with Baltimore. Looking through our priorities, we've got 700, 200, and 900. It looks like JFK is our best bet here, so we'll go there next. Okay. Okay, so processing its outgoing vertices, outgoing edges, 200 to Boston. Oh, that's better than 700, so we'll go ahead and update that. 600 back to O'Hare, but that's already been processed. We don't have to worry about that. Let's see, 1400 back. It's also a backwards path. We can ignore that. Okay, so continuing on, we'll finish off JFK, and we've got 2 nodes left. One has a weight of 200, the other has a distance of 900. So we'll pick the Boston, updating all of its outgoing edges. All of them have already been processed, so I'm going to ignore all of those. And then last, we've got Miami, which will take this path of 900, process all of its outgoing edges, although all of them have already been visited, and we're done. You might notice this is the same spanning tree that we had in one of our earlier examples.